Hello and welcome to another Wolfram Institute live stream. Today we have Floe Foxon, and Floe is a scientist and data analyst in the pharmaceutical industry, as well as a data science and statistics student at the University of Leeds. Floe will be presenting his project from the 2025 Wolfram Summer School, mining pockets of computational irreducibility with AI, transformer models of graph rewriting. Floe, go ahead.
Thanks, Dugan. Okay, let me share my screen. So thanks for having me. I'm excited to be here. Can you all see this okay?
Yes, we can see that.
All right, great. So I should say an alternative title for this presentation and project should probably be something like How I Learned to Stop Worrying About AI. It's a Stanley Kubrick reference, if you know it. I'm Floe. The link to my website is here on the screen if you want to look at some of my other work. Okay, so headlines. If you haven't been living under a rock for the last 3 years, you've probably seen headlines such as these that are pretty eye-catching. So Bill Gates predicts only 3 jobs will survive the AI takeover. Oh my goodness, within 10 years, humans won't be needed for most things. And even more recently, the AI scientist, fully automated scientific discovery. Well, this is pretty concerning if you have a job, especially if you're a scientist like me, being replaced by AI. So I think we need to scratch below the surface a little bit on some of these headlines. How can we investigate this? So there's an organization called Meta, and I'm taking a plot from their research here. What they've plotted here on the y-axis is the length of tasks measured by how long they take a human expert to complete. That can be completed autonomously, that is by AI, with 50% probability. And on the x-axis, it's the release date of the model. So, ChatGPT 2, GPT 3, and so on. So as you can see, and this is a log scale on the y-axis, by the way. So what they find is pretty much exponential growth in this AI time horizon. They conclude that the time horizon has doubled every 7 months, possibly accelerating to 4 months in 2024. And again, this is pretty nerve-wracking stuff with some scientific background to it. I should say that when they're testing, they're using standard benchmarks, tasks that are kind of set that they can give the model to complete. And they're showing it for different domains here with the different colored lines. If we take a little bit more of a critical look at this, though, notice that we're talking about a 50% success rate. Now, I don't know about you, but if I was at an organization and I was employing someone and they only had a 50% success rate of the tasks I was giving them, I'd probably be a little bit concerned. So they do have another plot here. I'm plotting this on the linear scale instead of the log scale. And this is whacking up the success rate to 80%. So, okay, a little bit better. But you'll see some of the confidence intervals for these point estimates of how well the models perform are really wide. So this is very recent. They just this month added Grok 4, which I've highlighted there. And you can see that, interestingly, Grok 4 actually performed worse than O3 and Claude 4, despite being released after them. So are we seeing kind of an end to this kind of growth? Maybe. Might be a little bit too soon to conclude that. But the 95% confidence interval for the performance of Grok 4 here was anywhere from 4 minutes to 42 minutes. So you've got, on the y-axis there, 15 minutes. If it's taking 3 times as long to complete the task, that's not great, with only an 80% success rate too. So, okay, how good is AI really? We have this interesting paper here on the archive by some authors from Apple. What they did is they gave a bunch of large reasoning models and large language models some controlled puzzle environments. So think things like checkers, towers of Hanoi, that kind of thing, things that humans can solve with a little bit of thinking. And they found that they give them different tasks, some easier tasks, some more complicated tasks. They found the models failed to develop generalizable reasoning capabilities beyond certain complexity thresholds. That for the simpler problems, the models were overthinking. They were really inefficient. It was overkill. And for the more complex tasks, they completely failed. So this is quite damning, actually, I think, this research. And similarly, here's another recent paper called What Has a Foundation Model Found? And what they did was, if you look at the figure on the left there, They got some data for the way that the Earth orbits around the sun. So you have, the relative positions of the Earth and the sun. And what they did is they said, okay, have at it, Hoss. We've given you the data. Go be Isaac Newton. We want this AI to be Isaac Newton and discover Newton's gravity. And what we find here is that it didn't perform so great. So if you look at the two figures on the left there, the rightmost figure, the red arrows or the kind of pinkish arrows are the predicted force. And those ought to be radially inward from the center of one mass to the center of the other. And as you can see, they are all over the place. So although the model was able to accurately predict where the Earth was, it completely failed to understand why it was there. The Newton force law for gravity is on the right there. You can see that the force is proportional to the product of the masses, and it's inversely proportional to the square of the distance between the centers of the two masses. And the force law that AI Newton figured out is not great. So it's not proportional to the product of the masses. In fact, one of the masses isn't even in there. It thought that one of the masses wasn't important. And we don't see an inverse square law in there either. If you were to give this to a physicist, I think they would say that this equation is not beautiful. Now, we can debate about whether or not beauty is a good criterion for finding physical laws, but I think we'd all agree that the one at the top is a bit more elegant than the one on the bottom there. And so we can extend this to discrete systems. So a discrete system, an example of that is cellular automata, which Stephen Wolfram is known for doing a lot of research on, pioneering research. And so what Stephen did with colleagues is in this blog post called Can AI Solve Science? Stephen took a autoencoder neural network and fed it some data on cellular automata and how they evolve with respect to time. And time or steps, you can imagine the steps as time. And we see that the correct kind of evolution is the top row of figures there. So this is how they're actually supposed to evolve. And the bottom row is, the black is the data that's kind of being given to the neural network, and the red or the orange is kind of how it's continued that trend forward. And you can see that for the really periodic cases, like the second one from the left or the second to last one on the right, it really nails it when there's some periodicity. Because it's quite simple. I think a human could have guessed that the pattern would go that way as well. But when you have the more aperiodic trends, you end up with kind of not a much less accurate prediction. And I would also like to mention the work of my fellow Wolfram Summer School student, Alex Fogelson, who did this really great blog post or Wolfram community post that you can read here at this link. Not to steal the thunder from Alex, I don't know if he's going to come on and present as well for the Wolfram Institute, but just a snippet of his work. When Stephen was doing this, he was actually not telling the AI what the rules were, just giving it the data and trying to let the AI figure out the rule for updating the cellular automata. What Alex did was said, okay, here's the rule. We're making it really easy for you, GPT. We're giving you the rule for the cellular automata. So go figure it out. What's the next step? And you can see that with GPT-4, it completely fails. Even when it's explicitly told how to update the cellular automata, it just doesn't get it. So now we're touching upon the topic of computational irreducibility and how that relates to prediction, which is one of the roles of science that we're interested in here and I've been talking about in the last few slides. So the idea of computational irreducibility is this idea of computation without shortcuts. If a process is computationally irreducible, it means that the outcome of a given process can't be determined easily ahead of time. The only way to find the latest state of the system is to explicitly compute each and every step in between along the way to get to that final state that you're interested in. But if you can find a pocket or a tunnel, so to speak, of computational reducibility, in other words, a shortcut, then maybe you can do accurate prediction. Maybe you can kind of skip ahead and boom, you know what's going to happen. So what my project attempts to do is extend these ideas to another kind of discrete system, right? We've talked about cellular automata, and now we're going to be talking about graph rewriting systems. And these form the basis of the Wolfram Physics project, which is why I was interested in them in the first place. So here's an example of a graph rewriting system. we start off, the graph is drawn on the left there. The adjacency matrix is just a matrix that tells you how the nodes are connected to one another. It's drawn on the right there. So this is a node, let's call it 1, and it's doubly self-connected. So that's what the adjacency matrix shows, is that 1 is connected to 1. Okay. We can take a given rule and apply it to this initial condition. I've taken the rule from the Registry of Notable Universes. It's called Wolfram Model 2717. And let's update it going forward a few steps. So if I press play here, and I don't know why that's not playing. Okay, and maybe I can just manually update it. So you can see the graph evolve, step 2, 3, 4, and so on and so on and so on. And you can see pretty quickly that this is difficult to predict, okay? If I was looking at this graph here, I wouldn't have predicted ahead of time that it would end up looking like this. And another thing to flag here that I think is important is that the adjacency matrix really blows up. So this is an example of a Wolfram model that grows exponentially. We started out with just one node, and we end up with, you know, more than 1,000 nodes at the end. After just, I forget how many this is, it's about 10 or 15 updates. So these are pretty difficult to predict. But wouldn't it be nice if we could predict them? Well, if you disagree, I'll tell you why. So one of the things we're interested in doing in Wolfram models is studying the time evolution of these models. But this can be really computationally intensive, right? Like I showed you on this previous example, the number of nodes blows up. And so the number of places that you can apply the rule becomes very, very large. The number of nodes that you have to apply it to becomes very, very large. This is computationally intensive, both in terms of compute, doing the update itself, and actually storing the graph as well. When you have so many nodes, the adjacency matrix actually takes up quite a bit of memory. So, but one of the things we're interested in doing with these Wolfram models when they evolve over time is looking at what's called their effective dimension. It's also known as the exponent of growth. And it kind of tells you what the dimension of the space is that you're working with. So if you imagine this as space and its exponent of growth with 3, we'd say that's equivalent to a 3-dimensional space. I have a quote here from Stephen's book, the Project to Find the Fundamental Theory of Physics. It says, if, for example, the effective dimension of the universe was initially much higher than 3, there will have been a much higher level of causal contact between different parts of the universe than we have deduced by extrapolating the 3-dimensional expansion of the universe today. So what's neat about this is it kind of explains inflation without inflation, does away with the need for inflation, which is kind of an unsolved problem in cosmology. So it would be pretty cool if we could predict the way that the effective dimension of these Wolfram models is going to change over time without having to go through, you know, the thousands of updates or whatever. So this is just one particular example, but there are many such examples of where it'd be interesting to study the properties over time or over updates, and kind of skipping ahead and predicting ahead of time would be potentially helpful for that. So the point of this project was to try and build a neural network for graph rewriting prediction. Essentially, we want a neural network that can predict the evolution of graph rewriting systems. And I say here forwards and backwards, because we also might be interested in taking the system back in time, right? The same way that we've deduced that the so-called Big Bang happened because we see the universe is expanding today. So extrapolating that backwards in time, we imagine the universe was at least the observable universe was much smaller in the distant past. So we're interested in looking backwards of the system too, potentially. And that may allow us to predict what will happen in the future or equivalent to the past of the system without having to explicitly compute all those steps in between, which I mentioned is computationally intensive. So what our neural network, our poor neural network has to do is learn the rule and how it's applied, which is a bit of a complication that we might touch upon potentially in the Q&A at the end. And it's going to do this by approximating this function f, which maps the state of the graph at step n to the state of the graph at step n plus 1, the next step, basically. This is a starting point. Potentially, you might be interested in relating it to the step at n plus 100 or 1,000 or 10,000, but for the basic starting, let's just try and predict the next single step in the evolution of the system. The weights W for this function are fitted during training, and we do that by minimizing a loss function. That's how training a neural network works. So the model we ended up using was a transformer model. I'll talk a little bit about some alternative models we explored as well, but for now, let's focus on this one. And I say we because Nick Murzin, who's here on the call today, and John Lederman, who are my mentors, were really instrumental in helping me figure out all of this transformer modeling. So thanks to those two. So we base this on the architecture of the generative pre-trained transformer GPT model, which exists in the Wolfram neural network repository. So if you have Mathematica, you can go and download that, same as I used. What this thing consists of is first an encoder or embedding module, which converts raw input sequences into tokens. Those are kind of chunks of input, and it maps or embeds these into what's called the feature space as feature vectors. And that represents some meaningful quality of the input. Okay, so the encoder embedding module is about finding meaningful qualities in the input. We say that tokens that have similar positions in the vector space, the feature space, have similar meaning. And what this helps us do is it captures contextual or positional information about the input. So in the example of ChatGPT, if you're typing, English language text in the input, it's finding meaningful relationships between words and letters and so on. Okay. So then after the encoder module, we have what's called the decoder module. And this uses multi-head attention. I'll explain what that is. I'll show you an example. What that does is it self-directs the attention of the network to the most crucial tokens. So the encoder is about finding the crucial tokens or the crucial chunks of input. And the decoder is about directing the attention of the network to those crucial tokens. Okay, and the net can be trained on input-output pairs. In our case, we're going to show it, the input is going to be the graph system at step n, and the output's going to be, the desired output's going to be the graph system at step n plus 1. So that's our input-output pair. And hopefully we want to learn something about their structure to produce the desired output, which will be our prediction. So I've actually got the GPT model from the Wolfram neural network repository imported here. So yeah, this is working, okay. So you can see first we have our what's called embedding. This is our encoder module. And you can see this here gets the contextual tokens. This part here is about the positional information that I mentioned. And then following that, we have the decoder module, which you can see is a sequence of, it's a chain of decoders. So we can take a look at one of these and opening it up, scrolling down. Okay, so you can see the attention mechanism is in here for one of these particular kind of layers in this sequence of attention mechanisms. And if we open up that attention, you can see it has all of these. These are called the attention heads. So I mentioned above that it's multi-head attention. So this is what I'm talking about. We have these multiple heads of attention all in parallel. And we can take a look at what one of those looks like. So this is our attention mechanism. Okay. Don't worry too much if you don't understand it. I barely do. But importantly, we take some input. We have an output pair that's associated with it. We want to find the important information in the input and hopefully get a good prediction from the model. So that's our transformer model. The first case we looked at for a graph rewriting system was periodic graph evolution. Excuse me for a moment. Okay, so for this periodic graph evolution, we made numerous simplifications. So essentially, we want to give the neural network the best possible chance at accurate prediction. This is a really kind of minimalist model. So we used undirected graphs, not directed graphs. We didn't use hypergraphs, which relate, more than 2 nodes. We've just got a regular graph. And what this does is it keeps nice symmetric adjacency matrices. So hopefully that would be easy to predict. And we're also conserving the node count. This is important. So our graph system isn't actually growing or shrinking. The reason for this is if I go all the way back here, and I mentioned that in just a few updates, this thing goes from having 1 node to 1,000 nodes. So this is very common in these Wolfram models, is that they have this exponential growth. I essentially will admit I did not have the storage capacity, the memory capacity on my ThinkPad to do this with a growing network. And in fact, I think many a computer would struggle with this. Essentially, you want to train a neural network with potentially thousands or tens of thousands of observations, maybe even more. And if you have exponential growth in your graph system, you're going to end up with so much memory usage that well, my ThinkPad couldn't handle it. So we went with one that didn't grow or shrink. The node count in the graph was preserved. The edges, the relations can change, of course. It's evolving over the number of steps, but it doesn't change the number of nodes themselves. So again, giving the neural net the best possible chance at prediction. So this is the graph system that we went with for the periodic case. You can see the rule here is that whenever you have something in the graph that looks like node A is related to node B is related to node C, and node C is related to node D, we want to turn that into this. Node B is related to node C to D, and D to A. And this is the initial state we took. So 1's connected to 2, 2's connected to 3, 3's connected to 4. This system has a period of 4, which again, I can play you here. I'll just manually do it myself. So this is the first step. Step 1, 2, 3, 4, 1, 2, 3. And again, we go back to the beginning. So a human looking at this long enough is going to figure out how the graph works, right? So you can kind of tell at each step, okay, I know that node is that edge is going to disappear next, and then that one's going to disappear next, and then that one. There are only 4 states, so a human could predict this very easily. And again, the adjacency matrix is there on the right just for reference. You can, once you look at this long enough, I came up with funny names for each of these. So this one I called the snake, because it kind of looks like, I don't know, kind of looks like a snake, the adjacency matrix, if you have an imagination. And I said the next step is that it goes down, and then it goes up, and then it goes middle, and then it goes down again. That was kind of how I was imagining it in my head. So if you've stared at this for hours and hours like I have, you can pretty easily predict what it's going to do next. Okay, so this is a very simple case. The transformer neural network, though, is picky about its input, so we had to format the input. So ordinarily in the Wolfram language, the graph looks like this. This is kind of the way it's represented, with these kind of inner braces representing each kind of node pair. And we formatted this, we just flattened it and added a delimiter in between the pairs of nodes. Why did we pick 100? Well, it doesn't matter what you pick, as long as that number is greater than the number of nodes. I know in this system there's only ever going to be 4 nodes, so we could have picked 5 or 6 or whatever, but 100 is a safe bet. So we never have a node 100, so the transformer should be able to figure out, okay, this is a delimiter, and it's always going to be there in between. Okay, so I mentioned that state n is used as the input, state n plus 1 is used at the output. That's our input-output pair for the transformer. So we generated 1,000 samples, 1,000 updates, if you like, from that initial condition. 800 of them we used for training, 200 we used for validation, so quite a bit. And you can see from the loss curve when we were training the model, it seems to have learned something, so fingers crossed. What do we get? Okay, in the case of forward prediction, the adjacency matrix on the left here is the actual adjacency matrix, so how the graph is actually updating with respect to time or the number of steps. And the right there is the prediction from the neural net. So how did we do? As you can see, pretty good. So this is actually perfect. It's able to predict every single next step perfectly. So, you know, maybe Meta are right. Maybe Bill Gates is right. Maybe we do have to worry about losing our jobs or something. In any case, in the periodic graph case, it's able to do forward prediction perfectly. It's able to do the prediction well. So fantastic. I mentioned earlier that you can do backward prediction, right? You might be interested in seeing what happens to the system backwards in time, if you like, or as the steps go backwards in the sequence. And it's able to do that perfectly too. So this time, instead of the, I don't know why here we go. So instead of the snake going down, the snake goes up. I know that's such a silly way of referring to it, but anyway, that's how I'm going to refer to it. The snake goes up. Yeah, okay. So that's the evolution, and you can see it. The neural network's predicting it perfectly. I'm only presenting the first few states here, but you could animate this for hundreds or thousands of states, and it gets it perfectly. It never makes a mistake. All right, so periodic case done. What about an aperiodic graph system? Well, what do I mean by that for a start? So we're looking for a system here, a graph rewriting system that doesn't cycle through the same states, ideally. We want it to have unique states at every opportunity. Now, the astute observer will note that for a finite number of nodes, there's only going to be a finite number of states. So you can't have a truly aperiodic graph if you're fixing the node count, and that's true. But again, we couldn't look at growing, exponentially growing, or even linearly growing graphs because I had computational limits with what I could do here. So I managed to find, this is the best, kind of the best I could do at the time I had, was this system, which is, it is periodic, but the period is greater than 80,000. I initially tried to, this is kind of an interesting anecdote, I tried to generate kind of 100,000 updates of this system on my laptop on one day of the summer school, and set it off in the morning. And I was like, this is great. By the time I come back from breakfast, maybe lunch, it'll be done. And as you can imagine, that's not how things went. And I came back later in the day, and it was kind of a sunk cost fallacy. I was like, oh, do I kill the kernel and hit stop? Or maybe in the next 10 seconds, it'll finish creating those 100,000. In the end, I actually ended up using Wolfram cloud computation to do it. So a computer in the cloud, so to speak, did it all for me overnight, which was nice. So I woke up fresh the next morning with 100,000 updates, and I thought, fantastic, let's make sure it's not periodic. And it was periodic. But the period was like 84,400 and something. So I figured, okay, let's just split the data set. Let's only train the network on the first 80,000 or so states before it becomes periodic, so that we're still forcing it to learn the rule, right? If I'd have fed it the whole 100,000, eventually it would have noticed probably and said, oh, look, state 1 is the same as state 85,000, and 2 is the same as state 85,001. Oh, okay, I can figure this out pretty easily. I didn't want that. I wanted to force it to learn the rules. So I didn't show it any of the kind of periodic portion of the evolution. I only trained it on that first 80,000 steps. And all that is to say, this is what the graph looks like. So step 2, 3, 4, you can see this is not easy to predict. I don't think it matters how long you would stare at this. No one's ever going to figure out that kind of, without having to explicitly apply the rule to all the nodes in the right order, you're not just going to guess what the next step looks like. This is not intuitive. The adjacency matrix on the right there as well, you can see the evolution of this system is not intuitive. It's not simple. It's aperiodic, more or less. I'm cheating a little bit, I know. But anyway, so we ended up training the neural network on this. This is what the rule was, by the way, in the initial state that we gave it. So there are 10 nodes in this system, and retrained the neural network on this 80,000 sample. And this is what you get. So I'm showing you the case of non-iterative forward prediction now. Okay, what do I mean by that? So ordinarily, what you'd want to do is you give it the initial state, step 1, call it, or 0, whatever you want. And then you get a prediction. You feed that into the model and get a prediction for the next step. And then you feed that prediction back into the model to get a prediction for the next step. And then you feed that prediction back to the model for the next step, and so on and so forth. I do that in the next slide, but for this slide, what I'm calling non-iterative prediction, I'm just showing it the previous state. So I show it state 1 to predict the actual state 1 to predict state 2, and then instead of putting the prediction for state 2 back into the neural net, I put the actual state 2 back into the neural net. So I truly am only predicting the next step here. It's not an iterative prediction process. Hopefully that makes sense. If not, then I apologize. So this is the result for non-iterative forward prediction. So it's just predicting the next step without feeding it back in. And you can see some of these adjacency matrix, well, there's something there. There's a resemblance between the actual and the predicted for at least some of these, not for all of them. But I think there's a couple towards the end there. Yeah, that looks pretty good. I mean, there's a couple of blobs here that it didn't pick up on, but yeah, this one's pretty good too. You can kind of see how if you made a couple of little edits, it would be pretty close. So, okay, maybe the neural net can do this aperiodic prediction too. So now let's look at iterative prediction, where we really are just feeding the prediction back into itself over and over and over again to predict the forward evolution of this aperiodic graph rewriting system. And you can see it really falls apart. So I'm just going to scroll through here, and you can see that the prediction on the right bears little, if any, resemblance at all to the actual graph state on the left. By the time we get to the end, the predicted case falls into a kind of periodic loop with only about a period of 5, and no resemblance whatever really to the actual. Again, I'll go through and iterate that. So starting with the same initial state, the actual on the left and the predicted on the right. And you can see, it's a shame the animation's not working when I click, but maybe I can get it working. In any case, so the prediction bears very little resemblance to the actual, so it's not doing great. And that's looking at the adjacency matrix, which is cheating a little bit too. If you really want to see how good the prediction was, you've got to look at the graphs. So we have the actual graph here on the left and the prediction on the right. And oh, what's going on? Why does node 2, why is it self-connected 4 times? Doesn't make a lot of sense. So the prediction's really not great for this particular transformer trained on data from this particular aperiodic graph system. So I'll animate that again, starting from the same initial condition, and you can see very quickly it falls apart and the prediction bears little resemblance at all to the actual. All right, then. So what can we conclude from this? What we tried to do is predict graph rewriting systems using neural networks. When you're using a simple periodic system, the prediction is perfect, chef's kiss. It's fantastic, no notes. However, for more complicated aperiodic systems, to reference American Psycho, it's not great. And that's just predicting the single next step was all I was trying to do, let alone if you wanted to predict the next 10 or 10,000 steps. So I think these findings comport pretty well with what Stephen and Alex found in their cases with cellular automata, another kind of discrete system with neural networks. So, okay, what is the big picture of all of this? What does it mean? Well, to state the obvious, easy to predict discrete systems are easy to predict, and difficult to predict discrete systems are difficult to predict. Did I say that right? I felt like I said difficult in the wrong place, but hopefully I didn't. Anyway, read this sentence. That's correct. So what this means, I think, is that AI is not really this magic box that can solve every problem. You can't just expect to take any old neural net, throw it a bunch of data, and oh, fantastic, we're going to get the right answer. I think it's limited by computational irreducibility, just the same way that humans are. Perhaps if you were to build a much better model than the very simple reductive model I had, and give it way more data, if you found a periodic system or an aperiodic system with a greater period, or a growing system that really is aperiodic, maybe a much better network would have cracked it, right? Maybe if I'd have used more neurons in the attention heads, maybe if I'd have used more attention heads, maybe if I'd have used more decoder layers in series, maybe. But this raises the question, at what cost, right? There's a big computational cost to this. The whole point of this was to try and see if we could find a shortcut. And I guess this question is not really often thought about, I don't think. But if the shortcut you're trying to find actually takes more compute power and more storage and memory and so on, than actually just updating the damn graph to the next step, what's the point? That's not a shortcut at all. That's a detour, I think. So it's kind of what I called it, a false pocket of computational reducibility. I don't know if that'll catch on or if someone's already coined that first. But yeah, I mean, if we go back here a little bit, so I at the very beginning with the growing graph, I mentioned just how many nodes these things have, and this is only after 10 or 15 steps. So, computing the next step from this state is probably actually less computationally intensive than building an enormous neural network, transformer, or some other architecture of neural network, feeding it in hundreds of thousands of observations, having dozens of attention heads and dozens of decoder layers and so on. There's probably actually a lot more effort than just calculating the next step, which was the whole point of what you wanted to do. So that's kind of the conclusion that I've come to with this. I just want to go back a little bit, something I forgot to mention. So I said that I would talk about some of the alternative architectures we considered as well. We tried a feed-forward neural network, and it worked pretty well for the periodic case. But it kind of, I don't know, it wasn't fantastic. We were ending up with these sort of, so the adjacency matrix here, these should be integers. And it was the feed-forward neural network was producing kind of floating point numbers, decimal numbers, fractions, if you like. And we didn't want that. You could pass that through a filter and make it so that you delete anything that isn't an integer, and then it looks nice and clean and it got the prediction right, but it's cheating a little bit. The transformer is more pure. And another thing you could do that we looked at least for the periodic case, if you really genuinely know that the graph is periodic, you can just use a classifier, right? Why not? If you know there's a finite number of states, then of course you can use a classifier. And there's a great function in the Wolfram language called, I think, classify, which is symbolic. So you can throw it pretty much any format of input and it will make a classifier for you. And that worked perfectly, again, at predicting this system. But that's also cheating a little bit, because by the very fact that you've used a classifier, you are kind of explicitly telling it, hey, there's a finite number of states. And the first thing it's going to do is say, okay, what are the finite states that I need to classify, right? So it's cheating a little bit. But the transformer was kind of the most effective and pure method that we worked on. So with that said, I want to acknowledge again everyone at the Wolfram Summer School 2025. My mentors were Nick Murzin and John Lederman. I also want to thank, of course, Stephen Wolfram, Stephanie, and all of the Wolfram Summer School 2025 faculty for their support. If you want to read some of the more computational details and look at the code, please don't. I'm just kidding. But if you do, here's a link to the paper here. So you can find it at this link on the Wolfram community. And that's all I had. I don't think I forgot anything. So yeah, I think we're ready for some Q&A potentially.
Yeah, thank you. Can you keep your screen up so we might jump around the slides for questions?
I can. I'm going to first close it and then reopen it and see if that fixes the animations. It's a shame that they wouldn't play.
That might be at the front end conflicting with Zoom somehow. I'm not sure.
Oh, it might be a problem with Zoom. Yeah, it was working earlier today, right before. It's just you know, the computer gremlins knew I was presenting.
Yeah.
All right, share. Do. Okay, maybe I'll keep it from going full screen as well. Let's try an animation. Yeah, there you go. Look at that beautiful animation. Shout out to list animate function in the Wolfram programming language. So yeah, you can see
well, now
this was the evolution
we can't
of
see
Wolfram
it yet.
model 271.
It's probably working well because you're not presenting yet. Hold on. Come on, Zoom.
But I did see it update.
Okay. Dugan's back.
Yeah, sorry. The Zoom cuts out sometimes.
And you're muted.
And I'm muted. Yeah, sorry about that. Zoom comes out sometimes. Okay. Yeah, speaking of the gremlins.
Yeah. They got to you. I jinxed you.
Okay, so slide 10. Yeah, so what do we... All right, we have a... Oh, yeah, that's showing a lot better.
Okay,
so these are... It's growing so fast because it's... I imagine that these are generations. That is to say that in between each of these individual frames, can you slow that down a little bit?
Yes.
Yeah. That it's doing multiple updates on the same rule between each of those, and it's like between each frame, it's doing as much as it can until it has to stop, until it can't do anymore, and then it spits out like the next like generational hypergraph.
Yeah.
Yep.
So, and then if you're, see, I'm wondering if that's also, you know, down the line with your more finite graphs of a fixed node size, if it's going by generations, then it's doing multiple updates per frame, and then that might be more difficult for a classifier to understand what the rule is.
Yeah. Yeah, for sure. I might have mentioned somewhere in the slide deck that not only does the network have to figure out what the rule is, it has to figure out the way in which it's applied, which is subtly different. Now, the default in the Wolfram language, it follows certain steps. So because we use the same steps, that same kind of way of applying the rule, if you like, each time, that's something that I think theoretically the network ought to be able to figure out. If you were doing it completely at random, like if you were applying the rule, the same rule, but applying it sort of at random in between generations, as you referred to it, in between steps, then it's not going to have any chance of predicting randomness.
Right, so you're saying if there's more than one place where a particular rule can be applied to a hypergraph, and then the way that Wolfram does it natively is to use some criteria to pick where to apply the rule.
Natively, yes, there is some criterion. Yeah, there's consistent criterion by default. You can set it to random if you want, I believe. I think I was actually having this conversation with James, who's on the call. Is that right, James? Am I misremembering the conversation we had?
Yeah, exactly that.
Yeah. So I think we looked into the documentation. There is a consistent, by default, it will apply the rule in a quote unquote consistent way. It doesn't do it at random by default. But yeah, it's an additional challenge for any model to figure out, including a human who was trying to predict the evolution of the graph. It's not just the rule that matters, but the way in which the rule is applied.
Right. So I think the way that and Wolfram does it, the function natively does it, is by it picks the oldest edges and updates them first.
And then
that's additional metadata.
Draw, then it does something else, and
yeah, so that's additional metadata that is not coming through on the adjacency matrices that you use for training the model on.
Well, we train the model on the kind of the graph representation. So
I see.
Trained it on this, not the adjacency matrix. We started off with the adjacency matrix. When we used the classify function to begin with, we were giving it adjacency matrices because classify is symbolic and it can take anything as input, including adjacency matrices. But it was trained on this representation of the graph, not the adjacency matrix. The transformer was.
I think Dugan's point is that even that information may be not enough to determine the actual order. If it depends on the actual previous step, it's like the Wolfram model by default maybe depends on the ordering function, but it may include some second order effect depending like what is the ordering function. Maybe it knows the previous where they did happen, so that it would pick out those edges to the right.
Yeah, that's a great point. And for this simple periodic case that it was able to predict, it's only doing one rewrite, one application of the rule at each time. So it made it really simple. It kind of didn't really have to understand the way in which the rule is applied. It pretty much just had to figure out the rule because there was only one way to apply the rule at each step. Whereas for the aperiodic case, now that I've got the animation working, yeah. So, like you said, it's far more complicated.
Now let's see on. So you're using that representation each time. You're not feeding in adjacency matrices to the.
Nope.
I wonder,
no, not for the transfer.
I wonder if it's possible to feed in adjacency matrices and see what happens.
Yeah. Yeah, certainly there are different ways of representing the graph that one could experiment with. I think another simple thing you could do, I'm not entirely sure, based on conversations I had with John Lederman, I'm not entirely sure that the delimiters here are necessary. It might be that, I mean,
that's true. So if you're
figure out that there are pairs.
since
Oh,
you
it's
are,
uniform necessary. If it's actual graph and all the edges are binary, then it's not necessary. But in general, should be.
yeah, I was just about to make that point. Yeah, you don't have to, you just keep it in pairs and then just know that every other pair is its own edge, graph edge.
Yeah.
So can you go to slide 21?
Slide 21. You're on the ball.
Hey,
There it is.
yeah. So you had an iterative forward prediction. Can you elaborate on that? So that's just saying like you feed in this thing and it'll say like what's the next one.
Yeah, I thought I might have butchered the explanation on this. Sorry. So, okay. When I was talking about the iterative prediction, you train the neural network. Okay, we've got a trained neural network, and then we want to make our predictions. So we just start with this first graph here. I know I'm sure. Well, I can scroll down. This first graph here, and that's the only real observation, if you like, that we feed into it. It takes that first step 1, and it predicts step 2. Then instead of showing it the real step 2, we just feed its prediction for step 2 back into itself to make a prediction for step 3. And then to make a prediction for step 4, we feed the prediction for step 3 into the model. And then to make a prediction about step 5, we feed the prediction for step 4 back in the model. So we're feeding the prediction back into itself. That's why I referred to it as iterative. Maybe that's not a great word. But I think the reason this works so much worse than the other version where you really do show it the real one at each step is that the errors are compounded, right? So any error that's produced in this first step here, so you can see there are a few errors. Those errors go on to dictate what's happening in your next prediction. And that's going to create more errors. And then the errors in this one go on to affect the next prediction and so on. So we're getting this compounding error effect, which is why as the number of steps increases, we're getting worse and worse predictions, essentially. So hopefully that makes a little bit more sense. Did I explain it better this time around? Or?
Yeah, I think so. Right, so it's like you're doing auto regression on this.
Yeah, exactly. Yeah, that's a nice word. Better than the one I was using.
And so the auto-regressive is hallucinating more than the
Yeah, I mean, it's basing its next prediction off the errors it made in the last prediction, and it's doing that over and over and over again.
Mhm.
So it's I don't know. I guess another analogy would be maybe this is a poor analogy as well. It's almost like prion disease in humans. It's like it's cannibalizing its own mistakes and then replicating those mistakes or something.
So when you trained the one that's on 4 vertices, and it just kind of like had this C shape that kind of kept rotating, and you said you produced a training set for that.
Yes.
And it had like a lot of states in it, and a lot of like updated like pairs. Like here's this initial state, here's the updated state. And you had like thousands of those pairs of states.
Yes.
On 4.
Yeah.
On.
Well, thousands. I say we had 1,000 total. There were 800 that went into training, 200 for validation, and so each one of those is a pair. So the first pair is going to be state 1 as the input and state 2 as the output. The next pair of that 800 pairs is going to be step 2 as the input, step 3 as the output. The next pair is step 3 as the input, step 4 as the output, and so on.
So I guess there are, if every one of those like pairs of states, right, is like you have a graph with 4 nodes and a couple edges are there, and then you have an output as being a graph of 4 nodes and the edges are there. And I would imagine that a lot of those states are like repeated in the training data.
Exactly. Yeah, lots and lots of repeats, because this thing only has a period of 4. So there are only 4 unique states. I mean, you're looking at them now on this animation. So yeah, tons of repeats. And so this is kind of, I would hope that the model would pick up on that in some way and say, okay, I know what's going on. I know the game here is that whenever I see this one, the next is going to be this one, because I've seen that however many dozens and dozens of times in my training set.
Mm-hmm. And did it memorize all those rules? Did it get the rule, or did it memorize all the inputs and just say like, okay, I only see like 4 different inputs and they're connected to 4 different outputs, and I see this like hundreds of times, so it learned it?
Yeah, it's a good question. How would you know? How would you know whether it's figured out the rule or whether it's cheating?
I guess you can.
You actually made the correct validation. If you just period 4, you should have just fed 3 training unique pairs and check whether it learned the fourth one.
Yeah, that's a good suggestion. All right.
Yeah, thanks, Ethan. Is there further progress you would want to take this project? Like, what would be kind of like next if you were to continue this direction?
Yeah, so I would say, as a suggestion, figure out how to split up those hypergraph evolutions that are generational into step-by-step things. I don't know if that's native functionality for the Wolfram model or not. Nick, do you know about that?
Which what actuals? What do you mean by splitting?
One update at a time instead of.
Well, you can do one update. Certainly, there's just one time parameter. It's just you need to create your data set this way instead of just say how many time steps you want to evolve your hypergraph. You just and produce at some time series. You just make a single step every time, so that it would not even remember what was the particular order and all that. Yeah.
I don't know if this gets to the point you're making, Dugan, but I guess another extension would be to, rather than using the ordinary state graphs, would be to do something similar like this with the multi-way graphs. I don't know if that's even feasible, but that would maybe kind of get to the point that you're making about how there are many ways of applying the rule, and that the multi-way graph is kind of every possible way, right?
Yeah, that's another point. It's like, okay, how many different ways can the same rule mutate this graph? And you feed in all those pairs into it, and you see if it learns it. And then I don't know what it would do for inference. Like, if it.
You can try stochastically. You can make a stochastic neural network that actually has temperature. And if you're going to sample predictions, it's not going to produce you a deterministic result. If you're going to sample it, the good neural network would be the one that would actually sample the whole multi-way system. So it basically writes in all possible ways, but it's kind of stochastic. So in a way, you can sample the steps this way. Something like that.
That's for the Wolfram Summer School 2026.
Make a note of that. You'll remember.
On slide
Okay.
16, how did you get the loss curve?
Okay, so this is the default that comes out of nettrain, the nettrain function in Wolfram.
Okay. So it's just based on the number of like input output pairs for training, and then the ones for validation. I guess it's checking the validation examples.
Yeah, I think that's.
And doing inference on them. And then... no, it's using the
Well,
the validation
the
examples,
input-output pairs,
and it's training on the training examples and updating its internal, updating the model weights until it, loses less. So it got down to like 1% error.
Yeah.
You can see from the curve that it's the validation set is actually intersecting the training set.
Yeah, it's a little hard to see, but they're overlapping. I don't know if I can zoom in. Actually, I can. Maybe that makes it bigger. Is that a little clearer?
Yeah.
Yeah.
Damaris is asking if you have any idea why node 2 captured the predictive system in the aperiodic case.
Can you repeat the question? Sorry, where am I looking?
I'm reading it off of the YouTube chat here. Any idea why node 2 captured the predictive system in the aperiodic case? Case 2, I guess, maybe.
Oh, case 2?
Damaris is saying node 2. I'm not.
Okay. I'm not entirely clear on the question. Sorry. Does anyone else have any ideas?
So, on this example, how did it do? How did the encoder do as far as making predictions here?
So this is these animations I was showing here are the prediction on the aperiodic case.
Mm-hmm.
So actual on the left and prediction on the right.
So it got some correct. Is that right?
It got some correct. Yeah. But I mean, some is not great. I mean, you can see that is like, I mean, to take a look at this, this is a kind of a worst case example. Is that I mean, so it knows that node 10 and node 1 are related to each other, fine. But it knows that node 7 and node 1 are connected to each other, fine.
Oh,
then I mean, it has some connections that just don't exist at all.
So Damaris is pointing out that in the aperiodic case, there was a node that got a lot of self-connected edges, and that might have been throwing off.
Okay. Sorry, I was.
So I guess when we look at the graph.
Yeah. This one down here. I don't know if you can see my mouse moving, but now I remember. I don't know. That's just the way it ended up predicting. I mean, I think it's a hallucination. I mean, whatever kind of imaginary rule it has in its mind, once it's made the mistake of assuming that node 2 is self-connected, maybe whatever rule it thinks it's gotten right, just whenever you have a self loop, it just sort of keeps that self loop. I mean, you can see that with the self loop with 10 as well. Once it thought that 10 was connected to itself, it's like, okay, I'm going to keep that going forward. So whatever kind of imaginary rule it thinks that it's gotten out of these data, it just so happens to be that it's having that effect on those two nodes. I don't know if there's any significance to that. I think it might be difficult to tell. These models are sort of, apart from the prediction it makes, it's not very
well, it's interesting.
It
might be getting confused, because if the rule was, okay, you have A to B, B to C, C to D, and that gets mapped to like B to C, C to D, D to A. And you start like saying, okay, well, if you make a mistake in that prediction, you say, well, I have A to A, then A to A, then A to A. You rearrange those symbols symbolically because it's giving like the symbolic representation, right, or like this list of numbers with the limiters in it.
Yep.
So if it's doing syntax on that, it might be doing something that makes sense, but it's like it just got confused. I don't know.
Yeah, I think getting confused is
like
an
if
understatement.
It's rewriting those three self loops into a different configuration of self loops on the same node. Could be the case, but
could be.
So the adjacency matrices for this, I mean, it would have a higher value on the 2 by on at index 2 too.
Yeah, and you can see that's why the colors change. It's because it's
Right.
the 2 is like a deeper color because that's representing a higher integer value. And
So
then
it's
the
normalizing all the
lighter kind
ones
of-
to be like a third or something like that.
Yeah, it only ever comes with integer outputs. This transformer, I checked that with the output. Like you'll never get like 1.3 comma 0.67 or anything like that. Yeah.
I'm just saying, like, array plot. When you're plotting out that array, it'll pick the highest number and like normalize all the other hues.
Oh right, yeah. That's
So
how
that
this array plot.
The
works,
brightest
right.
spot is always just the same value of orange in that case.
Yeah, correct.
Okay, cool.
Thanks, Damaris. Damaris was one of the other students at the summer school that I was watching, who also had a fantastic project, and I hope that she presents it.
Oh yeah, we're working to put that on the schedule.
Great.
All right. Does anyone on the call have any questions? If not, I'll go ahead and shut down the stream. I know that, what was it? Seeds of Light and Love really enjoyed all these graphs. Very nice, and they seem to be learning a lot. So.
Thank you. Sorry the animations didn't work at first. I'll have to check the YouTube comments after this. And all right, thank you, everyone.
Thanks for everyone who tuned in on the live stream, and thank you, Flo, for your